All right, let's get started with Lesson 8, Ka and Kb. Now, there's really an important and simple equation that indicates the relationship between the Ka and the Kb of an acid-base conjugate pair. That equation can be expressed by taking the Ka of the acid and multiplying it by the Kb, and that equals what is known as the Kw. And of course, you know that Kw at 25 degrees C is 1.0 times 10 to the minus 14. So, if you have an acid-base conjugate pair, and you know what the Ka for the acid is, and you need to happen to solve for the Kb of the conjugate base, you can use this equation to do so. As long as you know the Ka and the Kw, which should be 1.0 times 10 to the negative 14 at 25 degrees C, then you can solve for the Kb. Or vice versa. If you know the Kb and the Kw, you can find the Ka. So it's just a nifty, fast way of being able to do this. All right? All right, another important concept that the Kb and the Ka is related to is what is known as the pKa and the pKb. The pKa and pKb numbers or values can be used to identify the strength of the acid very quickly. To find the pKa, we have to take the negative log of the Ka for the acid. And that will give us the pKa of the acid we're looking at. So the pKa is based on a log base 10 scale. To make it simple to get numbers that we can quickly look at to determine how strong the acid is. We can also find the pKb by doing the same thing, by taking the negative log of the Kb, and the pKb numbers or values will determine how strong the base is, and we'll look at that in just a moment. Now, there is a nifty relationship between pKa and pKb, and that is the pKa, okay, plus the pKb is equal to what is known as the pKw. And the pKw is just taking the Kw value and multiplying it by the negative log. And it turns out that the pKw is 14. And will always be 14 at 25 degrees C. All right? So we can then set this, that the pKa plus the pKb is equal to 14 then. Kind of like what we saw the relationship between pH and pOH. And so if you know the pKa, then you can use this equation here to solve for the pKb. All right, gives us it's important. So make sure you have that equation down, memorized. Know these two equations as well to solve for pKa and pKb. All right. So what exactly do the pKa and pKb numbers represent? Okay, I'm going to erase some things here to give me some room. Fact is, I'll just erase all of this. You probably have more space in your notes than I do. All right. So first of all, we do know that the pKa is based on a logarithmic scale 1 to 14. All right. So we have, of course, all these other numbers and so forth that represent the pKa's, and the same thing for the pKb. All right. So what is a number 2 versus a number 3 pKa really mean? Well, it turns out that the larger the pKa value is, the weaker the acid is going to be. And the same thing with the pKb. The larger the pKb, the weaker the base. So we can kind of put this in a relationship terms. You got a strong acid, okay? Weak acids are down here. And so as the, essentially as the pKa as the pKa increases, the acid is going to get weaker. So a pKa of 3 versus a pKa of 2, the pKa of 3 is a weaker acid than the pKa of 2. Now, this is inverse of the Ka. The Ka increases, we get a stronger acid. So what we're saying is the Ka and the pKa are inversely related to each other. Large Kas mean we have a strong acid. Smaller pKas mean we have a stronger acid. Okay, so that's kind of the way to use the pKa. So again, here's kind of let's check your understanding. You got a pKa of 4 versus a pKa of 6. Which one is the stronger acid? That's right, the pKa of 4, because it's a smaller value. The smaller the value, the stronger the acid, which also means that it's going to have a larger Ka. This one will have a larger Ka than the other one. Okay, so just for your information, check for your understanding. Okay, so same thing with the pKb now. So we can have a strong base and a weak base. All right, so the same idea, the pKb increases, we get a weaker base, and it's just inverse of the Kb values. The larger the Kb, the stronger the base. The smaller the pKa values, the stronger the base will be. Okay, so again, if I have a pKb of 12 versus a pKb of 2, which one is by far the stronger base? Well, it's going to be the pKb of 2, because the smaller the number, the stronger the base. All right, so that's kind of how you can quickly use the pKa and pKb values to determine the strength of the acid and the base. All right, here's some other information you should know. pKa and pKb numbers are usually positive and they have no units. A change in a unit of pKa or pKb represents a 10-fold increase in the value of Ka or Kb. Okay, so in other words, what we could say, if you have a pKa of 2 and a pKa of 3, the strength of the acid is going to increase 10-fold as you go from 3 to 2. All right, so we could say that the acid that has a pKa is 10 times stronger than an acid at a pKa of 3. Okay, so that's important to understand. And then also the pKa's and pKb values are specific to a temperature, and so usually the temperature needs to be quoted for those. All right, so there you have it, the relationship between Ka and Kb for a conjugate acid-base pair, and what pKa and pKb, how that works, how we solve for it, and how it helps us to understand the strength of an acid or a base. So that is it for this particular lesson.